Hello, stat students. So today we are going to start Chapter 2 notes, modeling distributions of data. Recall that distribution of a variable is the value a variable takes and how often it takes that value. When working with quantitative data, we can calculate the position or location in the distribution by calculating the percentile of that value. The percentile consists of the percentage of values that lie at or below the value. When I finally get you guys the textbooks that you want, it'll mention how percentile is just below the value. Well, the new definition by the College Board that they want you to know is that it's at or below the value. Percentile should be whole numbers, so if you get a decimal, use your rounding rules. When you're looking at percentiles, it always mentions at, like at the 40th percentile. Here's an example problem. The stem plot below shows the number of wins for each of the 30 Major League Baseball teams in 2009. Find the percentiles for the following teams. A, the Colorado Rockies, who won 92 games. So if I find the Colorado Rockies, here's 92 games that have won. If you look at Colorado Rockies' position, there are 5 teams who scored more, who won more games than the Colorado Rockies. So you have to count the Colorado Rockies and everyone below that. So since they're in the 25th position, it's 25 out of 30. And if you calculate that, that's the 83rd percentile. The New York Yankees, who won 103 games, well, 103 is the max, so counting the New York Yankees, it's 30 out of 30 teams, so that's the 100th percentile. And you don't see that, you only see that because of this new definition. Okay, and then lastly, the Kansas City Royals and Cleveland Indians, who both won 65 games. So if we find 65 games, there's 2 teams. So counting those 2 teams plus the 3 below it, that's 5 over 30, which is the 17th percentile. And that's how you calculate percentiles. In Chapter 1, we talked about frequency charts and graphs that used counts, relative frequency charts and graphs that used proportions or percents, and now we have, in Chapter 2, cumulative frequency charts and graphs. The cumulative frequency chart and graph is directly related to percentiles. It tells you what percentage of the values lie at or below a certain value. We can also use this to find the first quartile, 25% below, the median, 50%, third quartile, 75%, along with the 5-number summary and the interquartile range. Here's an example problem. Here's a table showing the distribution of median household incomes for the 50 states and the District of Columbia. So if you look on the far left column, those are the intervals for the median income in thousands. So you have 35,000 to less than 40,000, 40,000 to less than 45,000, and so on. And the second column gives you the frequency that there's one household that had that income. There's 10 or I'm sorry, those are the states. So sorry, in the District of Columbia. So the relative frequency you get by taking 1 out of 51, because there's 50 states in the District of Columbia. Then the Next one would be 10 out of 51, and so on. That's for the third column. The cumulative frequency, so notice these two are related, but cumulative means that you're adding. So the very first one would be 1. The next one would be that 1 plus the 10 in row 2, so that's 11 total. And then you take that 11 and then add the 14, you get 25. 25 plus 12 is 37, and so on. And then you should end with 51. 50 states and District of Columbia. The cumulative relative frequency now would be related to this column. And so what we're going to do for this one is be 1 over 51, because these are your proportions or percentages. That's 0.02. The next one would be 11 over 51. That's 0.216. And I calculated all of these for you for the sake of time. And then 37 over 51. We're going to need those here in a little bit. That's why I'm writing these down. 0.725. 42 over 51 equals 0.824. 48 over 51 equals 0.941. And then lastly, of course, 51 over 51, you're going to end up with 100% or 1 here. We'll just round to 3 decimal places. All right, so with this, you can find the 5-number summary and the interquartile range. So let's go ahead and label these. So your minimum would be right here. Maximum would be right here. The 25th percentile, which is Q1, is going to be between these somewhere, so somewhere over here. So let's write Q1, 25th percentile. Okay, and then the median would be right around somewhere between, or here, 50th. Quartile. And then the 75th quartile would be right in here. So that would be your Q3. And that's how you would read the cumulative frequency table. The next thing we're going to do is we're going to take that information and we are going to look at a cumulative relative frequency graph. I think I called that a cumulative frequency table when I meant to call it cumulative relative frequency table. Okay, so now we are going to determine the 5-number summary from the graph. So actually from the graph if we didn't have the table. So if we look at the graph here, let's look at the title, the median household income along the horizontal axis, and along the vertical axis, you have the cumulative relative frequency. So those are your decimals that we had on the previous page. So we are going to take those main decimals, the 25th percentile, 50th percentile, 75th percentile, and then plot those, and also the minimum and maximum. So now this one's already drawn for you at 0, and right here, so I'm going to sketch this in if I can without messing up so bad. So here at 100%, you're going to have 70,000. And if you look at your table on the previous page, you'll see that 65 to less than 70,000, it's 100, 1.00. Now for the 75th percentile, so here is 60, 70, it'd be right around here, 75. Again, it's how decently I draw this. And then draw your vertical line down. So that'd be about 56,000. So I'm going to write down here 75th percentile, percent sign, ILE. And then we're going to find the 50th. So it would be right here. Oops. And then 25% would be Eh, I think more time is taken in notes by drawing things than anything else. So now that we've drawn those, we can determine the 5-number summary. So our minimum is 35, and you see that right here. There we go. Didn't draw that. Q1 is about 46,000, so we're just going to put 46 because we already know it's in thousands. And then median is 50. Q3, which is our 75th percentile, is about 56,000. Really, it's how you draw the line. You could have 57. It's okay as long as you show your work by drawing the information on your graph, and the maximum is 70. Interpret the third quartile from the graph. So here, the third quartile, 75% of the median household incomes for the U.S. are at or below $56,000. Remember, the steeper the segment of the graph, the more values that lie in that interval. So for instance, there will be more values here where it's steeper than it will be over here. All right? So that takes care of the cumulative relative frequency tables and graphs, and we've also talked about percentiles. Our next topic is standardized scores. This is known as the z-score. So another way to measure the position of a value in a distribution is the z-score. Now, what the z-score is, it measures the relationship of a value to the mean, and I'll get there here in a second. So it does that. It is a standardized location that tells you how many standard deviations from the mean the value is. So that's a relationship. Having a standardized location allows you to compare from different distributions of the same shape. So, for instance, if we're comparing heights of males in the US versus heights of males in China, and we have these two distributions, if we standardize, we can compare, say, Joe's height in the US versus Joe's height in China, where he might be one standard deviation above the mean in the US, he'd be 1.5 in China, meaning he'd be taller. So it just gives you a way to compare from different distributions of the same shape. The z-score is not measured in the same units as a variable. It is measured in standard deviations. And I know I can't fit that word in there. The z-score is also directional. A positive z-score tells you it is above the mean, where a negative z-score tells you it is below the mean. The number tells you how many standard deviations above or below the mean, and you have to mention that it's above or below to get full credit. And that's why we're going to do examples so you know how to do it. Note that all standardized scores will have a mean of 0 and a standard deviation of 1. A standardized distribution will have the same shape as the original distribution. So before you standardize a distribution, if the distribution is right skewed, it will remain right skewed. If it's symmetrical, it will remain symmetrical. Right, going back to our wins in Major League Baseball, in 2009, the mean number of wins was 81 with a standard deviation of 11.4 wins. Find and interpret the z-scores for the following teams. So in order to find the z-scores, we need to know the formula for the z-score. So here is the formula, and we want to write that. We can write that here in the sidebar. So the formula for z-score, and it is not on your AP formula sheet. It's something that you're expected to know because you learn it from the very beginning and you use it throughout, is equal to the value minus the mean divided by the standard deviations. So in statistical terms, the z-score is equal to the value is x minus, remember the mean is x bar, all over the standard deviation. And for the sample, it's S sub x. So that is our formula. So to find the z-score of the Yankees, their value is 103 wins minus the mean of 81 divided by the standard deviation, which is 11.4. And you do the division, you end up getting a z-score of 1.93. And how do I interpret that? So that means that the New York Yankees z-score is 1.93 standard deviations above the mean, meaning they did better than the average. So 1.93 standard deviations above the mean of 81 wins. Okay. And now let's do New York Mets with 70 wins. So the z-score is equal to 70 minus 81 divided by 11.4. That'll give you a negative value. It's negative 0.96. So what does the negative tell you? And remember, that's why we said when we're talking about standard deviations, you mention if it's above or below the mean. So the negative tells you it's below the mean. So, but you don't say negative 0.96 below. You just say 0.96 standard deviations below, because the negative is taken care of by the word below, the mean of 81 wins. Okay, still talking about z-scores. We're going to compare z-scores from for this sample problem. So two basketball players are arguing about who is a better player. One is a top rebounder that averages 12 rebounds per game. The other is an assist leader with an average of 8.7 assists per game. The distribution of average rebounds per game in the league has a mean of 11.3 and a standard deviation of 1.74. The distribution of average assists per game in the league has a mean of 8.1 and a standard deviation of 1.47. Determine who is the better player based on their stats. So let's first find the z-score of the rebounder. Let's label so we know and other people can read your stuff. So rebounder, the z-score is equal to, let's see, 12 rebounds per game minus the mean, which is 11.3. And you can always circle all this data in your paragraph. And the standard deviation is 1.74. So the z-score is 0.402. Now let's find the assister, I guess. So z equals, let's see, the assist player averages 8.7 assists per game. And the average is, let's see, there it is, 8.1 divided by the standard deviation, which is 1.47. And so the z-score is 0.408. So both are pretty close to each other. Both z-scores are close to each other, but the assist leader has a higher z-score. So we will determine that he is the better player based on the stats. So let's summarize that. Both are close to each other, but the assist leader has a higher z-score. All right, let's go to our last topic for 2.1A. The characteristics of speed and strength are considered to be of equal importance to the team in selecting a player for the position. Based on the information about the means and standard deviations of the speed and strength data for all players and the measurements listed in the table below for players A and B, which player should the team select if the team can only select one of the two players? Justify your answer. So it's similar to that last problem. You're choosing based on your data. So if we look at player A, you have the time to run 40 yards, and player A is faster than player B. It gives the mean and standard deviation for the time to run for each player. And then it also gives the strength or the weight lifted for each player and the mean and standard deviation for each as well. So let's go ahead and do the speed first. So let's do time to run 40 yards first. You want to write a little small here. Okay, so player A, his or hers. Okay, so the z-score, well, since weight lifted is 370, let's see there, that's a really strong woman. Okay, so the z-score is 4.42. That's the time run, minus the average, and this is player A's average, is 4.60 based on the table, divided by the standard deviation, which is 0.15. So player A's z-score is negative 1.2. Okay, now let's do player B. Okay, so player B, z-score is 4.57 minus 4.60, all divided by 0.15. So that gives me a z-score for player B as negative 0.20. Now let's look at that for a second. So you would expect, like in the previous example, that player B would be the better player in this case. However, we're going to look at the context. In context, the faster time, so in this case, the faster you are, the better you are. So you want a lower z-score. So you want a more negative z-score. So this person right here is faster, way faster, because we're interested in faster times. Now let's look at the same two players as far as strength goes. So we'll do player A. So I'm going to go over here. So the z-score, so I'm looking at the bottom row of my table, 370 minus 310 over 25. And that gives me a z-score of 2.4. For player B, we have 375 pounds minus the same 310 minus or divided by 25. And that gives me a z-score of 2.6. So now looking at those two z-scores, the 2.4 and 2.6 are pretty close together. So they're not, player B is definitely better in this case because player B has a slightly higher z-score, but not much better. So, and you can easily bring player A close to player B as far as strength goes, but as far as time to run 40 yards, there's such a big difference here that it would definitely make player A the better person to choose. So player A, and of course you would have to explain all this stuff that I mentioned, because you have to be able to explain your thought processes and why you're picking something for someone who's grading your exam, whether it's me or whether it's an AP grader or what have you. So you need to be able to explain it. Okay, we will pretty much end our, or that takes care of 2.1A. 2.1B is just on transformations. It's super short and it just covers the rest of 2.1. Okay, so transforming data. The z-score is just transform data. We can analyze the effects of transformations on a distribution, just as if you remember from Algebra 2, we did transformations of equations. So if we had a parabola that was y equals x squared, and we then shifted it 2 units up, it would be x squared plus 2. Or if we multiplied it, it would be y equals 2x squared, and so on. So transformations occur when you add, subtract, multiply, or divide all the values by a number. When you add or subtract by a constant, the shape and spread stay the same. That makes sense. So if we have a distribution and it's right skewed and the lowest score is a 4, if you're going to add 5 to each score, that's going to become 9. And the next one that was whatever it was is going to be added 5 to it. So it's just going to be shifted to the right 5, but the shape's still going to be the same. If it's right skewed, it's going to be right skewed. The center will change in the same way, meaning you add or subtract the constant. And I just mentioned that. And so will each location's value. And we'll do a sample problem here in a second. When you multiply or divide by a constant, the shape will stay the same. Oops. The center, spread, and location will change in the same way. In the same way. That means multiplied or divide by the constant. And here is our example. Here are a graph and table of summary statistics for a sample of 30 test scores. The maximum possible score on the test was 50 points. So you have a dot plot, and then you have the printout, in which gives you the 5-number summary, tells you how many data values there are, gives you the mean and standard deviation. Suppose that the teacher was nice and added 5 points to each test score. How would this change the shape, center, and spread of the distribution? So if you look at the table, if you're going to add 5 points to each test score, the mean, which is now 35.8, will become 40.8. The median, which is also a measure of center, because remember, the center is going to be added or subtracted by that constant. So the median is also center, so it would be 42. I guess we can write that down first. So the shape, and remember the shape will stay the same. So the shape and spread would stay the same. Oops. Because even if you're adding 5 points to every score, the difference, the range, the spread is going to be the same no matter what. Okay, so in other words, according to this graph in this context, and we want to mention this for sure. In other words, the shape will remain left skewed because that's what the dot plot shows. There we go. And the standard deviation and IQR would stay the same. So all your stuff relating to Q1, Q3, that's all going to stay the same. The mean and median would go up by 5 because those are your measures of center. Here we go. Part B, suppose that the teacher wanted to convert the original test scores to percents. Since the test was out of 50 points, how would this change the shape, center, and spread of the distribution? So you're going to multiply by 2, right? Because you're talking about percents here to get 100 points. So the shape stays the same. The center and spread would be multiplied by 2. Right. When combining transformations, write an equation to illustrate what is happening. Solve the equation for the other variable. Then apply the transformations. And the example we're going to do to end our notes is taxi cabs. In 2010, taxi cabs in New York City charged an initial fee of $2.50 plus $2 per mile. In equation form, the fare is equal to $2.50, that's the initial fee, plus $2 times mile per mile. At the end of a month, a businessman collects all of his taxicab receipts and calculates some numerical summaries. The mean fare he paid was $15.45 with a standard deviation of $10.20. What are the mean and standard deviation of the lengths of his cab rides in miles? So if we look at the equation form, the fare, so that would be $15.45 is equal to 250 plus 2 times the number of miles. And let's just use the variable m. Subtract 250 on both sides. And we have 1295 equals 2m. Divide by 2. M equals 6.475. So the mean is 6.475 miles. What are the mean fare he paid was $15.45 with a standard deviation of $10.20. What are the mean and standard deviation of the lengths of his cab rides in miles? Okay, now, so that's the mean. To do the standard deviation, okay, so mean is affected by addition and subtraction. Standard deviation is unaffected by and addition and subtraction. It's only affected by multiplication and division. So if we go to this equation right here, for standard deviation, this is irrelevant. So we just want the fare. So the standard deviation was $10.20. So $10.20 is equal to 2m because we don't care about the 250. That's just adding. So divide by 2 and m equals 5.10. So the standard deviation is 5.1 miles. So we don't subtract the $2.50 because subtracting a constant from each observation doesn't change the spread. So we might want to write that down somewhere. So don't subtract 250 because subtracting a constant from each observation doesn't change the spread. And that's it for 2.1A and B. Have a great day, stat students.